Swayam Prabha. Digital India. Educated India.
In the last lecture, we had started discussing on systems with constraints. We will continue that in this lecture as well. We had looked at the method of Lagrange multiplier to deal with constraints in our Hamilton's principle, and we have seen how to derive the equations of motion for systems with constraints. In this lecture, I am going to look at the interpretation. I am going to discuss the interpretation of the Lagrange multiplier that we have found. Let us go through a little bit of what we had discussed. We had the Hamilton's principle, but with now constraints, and the principle says the variation of the action must vanish, but we have these constraints whose variation also must vanish. Here for mechanical systems, the Lagrangian is the kinetic energy minus the potential energy. We had combined the variational statement with the constraints using the Lagrange multiplier, and for every constraint we had one Lagrange multiplier. And now this statement is the combined statement must be 0, must vanish. Look at the expression of this combined statement. The dimensions of delta L or delta L, this is energy, because it is for mechanical systems it is kinetic energy minus potential energy. Therefore, delta L has dimensions of energy. Therefore, this lambda dot delta C must have dimensions of energy. This must have dimensions of energy. Therefore, both our terms must have dimensions of energy, and from here we are going to interpret what is lambda. Now, what is lambda vector, which contains as many Lagrange multipliers as the number of constraints? Lambda vector dot delta C vector, which can be written as this summation, dot product can be written as summation using this expansion, because delta C j for the jth constraint can be written like this. This I have introduced in this expression, and I write it as a summation. This is my summation, and I am using this expression of delta C in there. If I rearrange these terms, I pull out that summation over I and bring in the summation over j here, and what you notice is this term, which has dimensions of energy, must be a product of some quantity and variation of my physical coordinates, and physical coordinates usually are displacement, linear displacement, angular displacements, right. In other words, we can make a very easy guess that whatever is sitting here in the brackets must have dimensions of the corresponding force. In other words, if it is a linear displacement, then the bracketed quantity must be force to make lambda dot delta C having dimensions of energy or work. If delta R I is an angular displacement variation, then the bracketed quantity must be moment. So, this is how we can easily interpret. So, this is our force. Now, force along the ith coordinate direction, and it could be force or moment. Remember that depends whether delta R I the coordinate Ri is a displacement coordinate, or it is a linear displacement coordinate or an angular displacement coordinate. Therefore, we call this as the generalized force. This generalized force is coming out of what? It is coming out of constraints. Therefore, these must be our generalized constraint forces, and delta Ri is nothing but the variational displacement of the ith coordinate. If it is a linear displacement, then our force must be normal force that we usually use, but if it is an angular displacement, it must be moment. I can write this as summation of q I c, that c in the superscript indicates that it is arising out of the constraints, times delta Ri. So, it is a again can be written as a dot product of our generalized constraint force vector and the generalized or our physical virtual displacement vector. This is our generalized constraint forces, and this whole dot product has dimensions of work because it is force dot displacement. Therefore, it has dimensions of work, and this is virtual work because it measures work due to virtual displacements of the physical coordinates. Therefore, this is virtual work done by the generalized constraint forces under the variation delta R. What we conclude therefore is the generalized constraint forces. What is the purpose of these constraint forces? These constraint forces maintain the constraint, just like in the example of the pendulum what we had looked at in the last lecture. The constraint forces, they maintain the motion of the bob on a circular path. Generalized constraint forces maintain the constraint, they are responsible for maintaining the constraint, whatever it takes to maintain the constraint, that comes from the constraint forces. The next thing is how we can find out the constraint forces. I have demonstrated. We first define a problem with constraints. In other words, if you want to determine constraint forces, you have to introduce a constraint. When you have to determine a constraint force in the Lagrangian approach, in the analytical dynamics approach, you first break a constraint and introduce the constraint as a mathematical quantity which must be maintained, and the corresponding Lagrange multiplier helps us in finding out the constraint forces. Therefore, we have to define a constraint problem to allow the constraint force to do some virtual work. We have to allow this constraint, we have to break the constraint and allow the constraint force to do a virtual work, and finally we put back this constraint, calculate the Lagrange multiplier, and from there we can find out the constraint forces. This is our approach. Let us revisit the pendulum that we had looked at in the last class. Physical coordinates, we did not use the generalized coordinates because now we want to let the bob break the constraint. Therefore, I consider that the coordinates are x and y in general, and we introduce this constraint x square plus y square is equals to L square, where L is the length of the inextensible string or rod, and we define the Lagrangian in the usual manner. Now, velocities are x dot and y dot, therefore, the velocity square will be x dot square plus y dot square as I have written. The potential energy expression V is equals to mgy. Here once again we have this Lagrangian, so kinetic minus the potential, and these steps we had discussed in the last class, and we had come up to this point that we had derived the equations of motion. We had then two equations of motion, one each for x and y, and we had the constraint. So, these are the two equations of motion and this is the constraint. And we had taken the variation of the constraint, this was the form, and also solved for the Lagrange multiplier, and this was obtained. Up to this we had discussed in the last class. Now, we are going to interpret. Now, the virtual work done by the constraint forces is given by lambda delta c. In this case, we have only one constraint, therefore, the dot product is just lambda times delta c. There is only one Lagrange multiplier, lambda delta c, and this is what we have. We have all the expressions. We have the expression of lambda written above, expression of delta c. I have taken the product of these two, and this must be in terms of the constraint force vector, this must be of this form. This is the constraint force vector and this is the virtual displacement vector, and the dot product of these two should give me the virtual work done by the constraint forces. And what do I therefore have from this expression? It must be that this expression must equate to q c in the x direction delta x plus q c in the y direction delta y, which follows from this statement. And I can read out, now I can read out q x c must be the coefficient of delta x, coefficient of delta x. Therefore, it is this multiplied by x, that is what I have written here, and similarly q c y must be coefficient of delta y, and coefficient of delta y is the same quantity times y, and that is written here. So, these are our expressions of q c x and q c y, the constraint forces, force components in the x and y directions. Now, from here how do I calculate the tension? Who maintains the constraint? In the case of a pendulum, who maintains the constraint? Who maintains the circular path? It is the string. And what is the force that maintains this circular path? The tension in the string. Now, I should be able to find out what is the tension in the string from these expressions of q c x and q c y. And how do I do that? I can write the constraint force whose magnitude is this curly t times the unit vector in that direction of the string written in the x y coordinate system that I have chosen, and the sin theta cosine theta I write in terms of x, y and L. This is straightforward. Now, I compare this with the expressions of q c x and q c y. If I do that, I can very easily actually find out the magnitude. This tension value is nothing but the magnitude of q c, and this is nothing but under root of q c x square plus q c y square. So, under root of this quantity is the magnitude, and that is the tension. And if I do that, I will get this simplified expression. You can very easily check this, and if I write in a slightly rearranged form, what I have done is I have taken this negative sign with y over L, so that I can interpret minus y over L is nothing but this cosine of this angle, minus y over L is nothing but cosine of that theta. Therefore, we have the component of the weight, a component of the weight along the string and the centripetal force. which you can very easily recognize from here. It is mv square by L. Therefore, we have found the tension, the constraint force. Let us then proceed to our second example, pendulum on a driven cart. We would like to find out the force that drives this cart in order to produce a motion which is specified like this, where u is some function of time, given function of time. It could be some sin omega t something, some function of time, explicit function of time, which is given to us. I would like to know how much force is required at the actuator to produce that motion of the cart. We come to the physical coordinates because we have to break the constraint. What is the constraint? Constraint is x must follow this motion profile, x must be equal to u of t. I break that constraint. I take x as a coordinate, I take theta as a coordinate. If you recall, if one of these see x is given in terms of time, explicitly as a function of time, we were not taking it as a coordinate, but now I am going to take it as a coordinate in order to break that constraint and allow the constraint force to do a virtual work. Our physical coordinates are x and theta, and our constraint is x minus u of t is equals to 0. I will write the Lagrangian in a usual manner. Only thing I have to remember that velocity of the cart is x dot, and the pendulum bob's velocity, we have found this previously. It is given by this expression. Therefore, our kinetic energy is ready. The potential energy, considering the x axis to be the datum, is minus mgl cosine theta. So, theta and x are our physical coordinates. We will write the Lagrangian. We have the Lagrangian and the constraint. The governing equations, we have derived this before. Our governing equations are obtained in this form. We will take one by one, and along with this the governing equations, we have the constraint. Here we have 3 equations, and we have 3 unknowns, x, theta and lambda. We will look at it one by one. The x coordinate first, this is the equation corresponding to the x coordinate. We find out all the terms, del L del x dot, ddt of del L del x dot, which we have done before actually. Del L del x is 0, and now the constraint del c del x. You have the constraint in front of you, del c del x is 1. And therefore, our equation of motion for the x direction, x coordinate, is written here now. These are steps I leave to you. Similarly, for the theta coordinate, we have this as the equation, del L del theta dot. We have derived this previously also, ddt of del L del theta dot. Del L del theta has a contribution, but del c del theta, you can see that the constraint does not involve theta. Therefore, del c del theta is 0. Our equation for the theta coordinate is written here now, straightforward, which I can simplify one step more. Now, what do we have? We have the first equation corresponding to the x coordinate, the second equation corresponding to the theta coordinate, and our constraint. We follow the steps that we had discussed before. We derivate the constraint, use the equations of motion. I use the second equation of motion, the theta equation, to find out theta double dot, and now I will use this in my first equation, this as well as x double dot in my first equation. And when I do that, I can solve for lambda, our Lagrange multiplier. Now, we have solved for lambda. How to interpret lambda now? Because we have to find out, remember, we have to find out the actuator force. Work done by the constraint force is lambda times delta c. And what is delta c? The constraint is already in front of you. Delta c is nothing but delta x. Therefore, it becomes lambda times delta x, and that must be equal to the dot product of the generalized constraint forces and the variation of the coordinates. You will notice that from our problem there is only a delta x contribution. Therefore, our constraint forces in the theta direction does not exist, it is 0, it must be identically 0. What exists is only the constraint force corresponding to the x coordinate, which is the displacement of the cart. Okay, done this far. Now, who is doing this work? Let us ask this question, who is doing the work? If when I break the constraint, what is the constraint force? We have broken the constraint means what? We have kind of removed the actuator, and who is doing that work? The actuator force, of course. The actuator force is doing the work. When I put back the constraint, the actuator force has to maintain that x coordinate as u of t, some given function. Therefore, this lambda times delta c, which is work done by the constraint forces, must be equal to f times delta x, which means our QCx must be f, the actuator force. And we can now very easily read out what is our actuator force. Actuator force is nothing but the lambda itself, but this is a very special situation. Lambda in general may not have the dimensions of force, but in this case it does. In this case lambda has the dimensions of force, but in general it will not have the dimensions of force. Now that we know the actuator force, the equation of motion for the theta coordinate is here, and the actuator force is nothing but lambda. Therefore, we have the actuator force, and you will notice here that it depends on the given time function. Of course, it will. The actuator force will depend on the given time function and of course, the coordinate theta. Our two equations are therefore only here. We have eliminated x by using the constraint, and also in the process determined lambda, and that happens to be the actuator force. To summarize, we had looked at the problems with constraints. We have used the method of Lagrange multipliers to find out the equations of motion, to derive the equations of motion, and remember I had discussed a most general way of deriving the equation of motion including the constraints, and that we have used today in the example. And finally, we discussed the interpretation of Lagrange multiplier, how that can be used to find out the constraint force. Remember that Lagrange multiplier need not be the constraint force. Lagrange multiplier is proportional to the constraint force. So, with that I will conclude this lecture.